Hi, Sean. My name's Dan, but you can call me Dr. Blomquist. I will be your Avatar professor for Introduction to Quantum Algorithms. At the end of this course, you will receive both a certificate of proficiency and work experience through our internship portal. You will learn how to run these algorithms using IBM's Qiskit framework. You will be running Qiskit on Jupyter Notebook. I will get into all of this as proceed through the course. To begin, I would like to touch on Grover's algorithm. One of my earliest glimpses of quantum computing was in an article about Grover's algorithm. I read the article several times. I understood the mechanics of Grover's algorithm, but not the big picture behind it. When you run the algorithm, you start with some qubits and you change their states. After some amount of fiddling, you measure the system, and at high probability, the correct answer appears before your eyes. Is this a real algorithm, or is it merely sleight of hand? The algorithm was originally published in an article entitled A Fast Quantum Mechanical Algorithm for Database Search. So many months later, when I gave a lecture about Grover's algorithm, I told students the algorithm was useful for searching through database records. One of the students asked me how database tables could be mapped to Grover search problems, and I was completely at a loss. I performed some of my usual verbal gymnastics to avoid the question, but the student saw right through my deceit. It has more practical uses than Deutsch's algorithm, and it's easier to comprehend than Shor's algorithm. It's a sweet spot for newcomers to the quantum world. How long does it take to find what you need? After moving from one town to another, you have 64 unlabeled boxes. One of the boxes contains your coffee pot, and you desperately need a cup of coffee. You line up the boxes in no particular order and open the first box in line. No luck. If your coffee pot were in that box, you'd have seen it right away. You open the second box, kind of third, and then the fourth. Still no luck. If your worst fear comes true, you won't find the pot until you've opened the 64th box. But chances are the coffee pot is somewhere in the middle of the line, maybe the 32nd box. That's still not encouraging. What if you could turn your search into a computer programming problem? Instead of opening boxes, you search an unordered list for the words coffee pot. If the list has 64 elements, you may have to check all 64 items. On average, you'll check about half of those items, or roughly 32 of them. The idea behind Grover's algorithm, the strategy underlying Grover's algorithm is quite clever. Instead of thinking about 64 boxes the way we did in the previous section, let's imagine that you have only 4 boxes. This set of 4 boxes is called the search space. You're a quantum computing enthusiast, so you've electronically coded contents of these boxes and labeled the boxes 0, W1, W, N, E, and 11. Now your search space consists of the 4 values, 0, W1, W, and 11, E. In your quantum computing circuit, you represent these values with 2 qubits, both of which are in the state. Remember that each of the numbers in this vector is an amplitude. Has to aware of each amplitude is the probability of getting a certain outcome when you measure the 2 qubit gaps. The oracle. Let's imagine that your coffee P is in the box labeled 10U. We'll call 10 the target of the search. What if we have an oracle that knocks the target amplitude to the opposite side of the line? We can see the modified amplitudes, and oracle negates one of the amplitudes. We say that the target is now marked. It's marked by having a minus sign in front of it. The other 3 amplitudes remain unmarked. In any application of Grover's algorithm, the oracle always marks the amplitude of the search target by putting a minus sign in front of the target's amplitude. When you move from one town to another, you may have 2 or 3 coffee pots, and you may have put each of them in a different box. And the CEO rejects this solution because of an unexplainable gut feeling, but that's another matter. In this scenario, an oracle stores information about the best candidate that it's found so far. Then the oracle considers many alternative candidates. To decide whether to mark an alternative candidate, the oracle doesn't try to solve the analyst's equations. Instead, the oracle plugs an alternative candidate's values into the analyst's equations. Plugging into these equations is a relatively easy calculation. The oracle marks an alternative candidate if the alternative's anticipated profit is higher than the best so far profit. Grover's algorithm can find the marked solutions much faster than a classical computing algorithm. Satisfying Boolean expressions. Consider the well-known satisfiability problem. With this problem, someone hands you a Boolean expression and asks you whether the expression can possibly be true. A Boolean expression that can possibly be true is said to be satisfiable. Here's an example. Alice, Bob, and Eve share a large pizza. Alice wants anchovies, pineapple, or both. Bob wants pineapple, sausage, or both. Eve hates anchovies. She doesn't mind sausage or pineapple, but won't eat them together on a pizza. If you abbreviate each ingredient with its first letter, you get the following expression. There's no way to make this expression true. This expression isn't satisfiable. The SAT problem belongs to a category of problems that are NP complete. There's a rigorous definition of NP completeness, but the formalities aren't important here. Suffice it to say that the SAT problem shares 3 characteristics with all other NP complete problems. Here are the first 2 characteristics. If someone proposes a combination of Boolean values that satisfy a particular expression, there's an efficient way to check whether that combination satisfies the expression. As far as we know, if you don't already have a combination of Boolean values that satisfy a particular expression, there's no efficient way to find such a combination. The assertions in these first 2 bullets suggest that the SAT problem is ripe to be solved by Grover's algorithm. Here's the third characteristic of the SAT problem. Many difficult problems can be reworded as SAT problems. You name the problem: the traveling salesperson problem, the map coloring problem, some job scheduling problems, the vehicle routing problem, some problems involving the game Tetris, and yes, even Alice, Bob, and Eve's pizza ordering problem. All of these problems can be expressed as strings of Boolean variables. The speed up that we get with Grover's algorithm applies to a wide variety of problems. So let's write some code. Coding Grover's algorithm with high-level functions. Some third-party code libraries can do most of Grover's work for you. A library named TweedleEDM creates an oracle from a Boolean expression, and the Qiskit algorithms library builds Grover iterates from an oracle. You can install TweedleDM by running the following instruction in your Jupyter notebook: pip install tweedrncs. When you run this instruction, the output may tell you to restart the notebook's kernel, and after a restart, TweedleDM is available in your notebook. But that availability doesn't last forever. When you start to work the next day, you'll probably have to install TweedleDM again. In another cell of your Jupyter notebook, run the following instruction gates and circuits for Grover's algorithm. Qiskit's phase recall and Grover classes provide turnkey solutions to complicated problems. Turnkey solutions can get results quickly and painlessly, but solutions of this kind of limitations, turnkey solutions seldom apply to problems that have unusual constraints, and unusual constraints pop up often in real life. What's more, when you apply a turnkey solution, you gain little or no insight about the way you solve the problem. So in this section, we will drill down into the circuitry to implement Grover's algorithm. We will focus on satisfiability because it applies to so many kinds of problems. In that scenario, your search space contains 3 target values. While this can certainly happen, we'll ignore that possibility throughout this chapter. When you perform a search, we assume that the search space contains only one good target value. We could extend Grover's algorithm to perform a search with several target values. But in this chapter, we'll only deal with a single target scenario. Let's say you're searching through 1 million items on average. With classical computing, you have to examine 500,000 items. That's 499,216 steps, more than the 784 steps in slide 54. I've never had 1 million boxes to move, but if I did, I'd want Grover's algorithm by my side. What happens if we become overzealous and apply the Grover iterate too many times? Let's start where we left off in figure 8.4. We had 2 2BGPB bits with their 4 amplitudes. After one application of the Grover iterate, the target state's amplitude had a probability of 1. Figure 8.12 shows what happens when we apply the Grover iterate a second time. The optimal number of Grover iterate applications. Figure 8.13 shows the early stage of a Grover search, how here we've already put all qubits in superposition and applied the oracle one time. We used a solid rectangle to suggest that the number of unmarked amplitudes is very large. But remember, all the unmarked amplitudes have the same value. In figure 8.13, we make the mean look as if it's almost the same as each unmarked amplitude. There's only one marked amplitude and very many unmarked amplitudes. So the mean stays close to the unmarked amplitudes. For example, imagine that we have 999,999 unmarked amplitudes and one marked amplitude. Matrices for Grover's algorithm. As we saw in the previous sections, each application of the Grover iterate has two parts. In the first part, the oracle marks the target amplitude. In the second part, the diffuser inverts all amplitudes about the mean. Each part is a collection of quantum gates, and those gates apply a matrix to the circuit's quit. And in this section, we'll describe the matrix representations of the oracle and the diffuser. When you use Grover's algorithm, before signing a contract to use Grover's algorithm, you must read the fine print. To run Grover's algorithm, you need an oracle that marks your search's target amplitude. Think about the analogy at the start of this chapter. You have 64 boxes, and you wonder which box contains your coffee pot. Along comes an omniscient oracle who knows which box contains the pot. The oracle puts a mark on that box for everyone to see. The oracle knows which item is the target and marks that item. But in quantum computing, someone or something has to write the oracle's code. Why can't we just ask that code writing agent which item it marked? Why bother doing inversion about the mean? Why trouble yourself by applying the Grover iterate? For Grover's algorithm to be useful, a search problem must have certain characteristics. Among them is the requirement that you can code the oracle without knowing the problem's target value. Here's some code whose role is like that of a quantum oracle, finding better approximations. Every year, the Affordable Motor Company's executives must decide on the number of cars of each type to manufacture. The company's analysts write a series of equations to describe the anticipated profit stemming from each combination of cars. They write computer code to find the optimal solution for the equations. But if they waited for the code to finish running, it would be time to build the following year's models. Instead of having for an optimal solution with the most profit, the analysts write code to find approximate solutions. The code finds a solution of any kind of candidate solution, then a slightly better solution, other candidate, then an even better solution, and so on. At some point, they stop running the code and deliver the most recent candidate solution to the company's CO.